In this video, we take a look at comparison of series, the next section, in determining how a series converges or diverges. And that's indeed the main focus for us here. It's whether or not a series converges or diverges, as opposed to actually finding the sum of the series. Okay, so for us so far, we're able to determine when a telescoping or geometric series converged or diverged, and then we were actually able to find the sum. We saw then in the last video, the last section, the integral test, and that test wasn't as specific. It just told us whether or not the integral and the series that we were working with converged or diverged. It didn't tell us exactly what the sum was, because though we could find the result for the integral, the series and the integral are different things. So just because the integral might have come out to be 12, that doesn't mean the sum would have actually been 12. So that's going to continue as we go forward here. In this section, we're not going to be able to find the actual sum, just whether a series converges or not. Okay? And the idea for this section is, of course, a comparison. We learned two methods in this section, two new tests. The first is what we call the comparison test, or the direct comparison test. And the second is the limit comparison test. Okay, these two are similar. I kind of think of limit comparison test as kind of a fallback, or something that we can do when the comparison test doesn't work so well, or is maybe difficult. But both of these tests basically will be used for series that are like something, basically like geometric like series or P series like series. Okay, so they won't exactly be geometric or won't be P series. They'll be close, but they're like those series, and we'll compare them to those similar series. For example, here, if I have the sum from 1 to infinity of 1 over 3 to the n plus n, I can kind of dissect this series, and if I look at this 1 over 3 to the n, that's geometric. And if I look at 1 over n, that's our harmonic series, or our P series when P is 1. And it's like both of those series, but it's not exactly both of them. It's geometric and P series like. But we can't just say, since the geometric series converges, we can't just say that this converges because the geometric series converges, or diverges because the harmonic series diverges. And first of all, that's contradictory, right? I mean, we can't have converges and diverges. This is like one or the other. It's kind of like both, but it can't be both convergent and divergent. So we have to find a way to basically compare this to one or the other and determine which series it's more like, if that makes sense. Or and then from there, if it's more like the geometric series, then we can say that the series does indeed converge. So what we do is we compare to these series. We always compare to a series, these other series, that we know the convergence or divergence of. Convergence or divergence of. We don't just compare to some random series, and you'll see what I mean a little later, I think, but we compare to a series that we know the convergence of. So it's got to be geometric. It's got to be a P series. It's got to be a telescoping series that we can compare to, though that's not typically one that we do compare to. Okay, so let's look here. What this gives us is what we call a direct comparison test. Okay, and I'll lay out the test here, and then I'll actually apply it. I'll use it. But what the direct comparison test says is the following. Let A and Bn be nth terms that kind of go in this order, right? So we have that an and bn are both bigger than 0, right? But that an is smaller than or equal to bn for all n, okay? Then I have two results from this. if the sum of Bn converges, if the larger series converges, then the smaller, the sum of An, should also converge. So that's basically like saying I have a larger series that converges, it approaches some number, then any series of numbers that I add that are less than that should also converge, right? I'm adding smaller things. So if I have a larger convergent series, that means the smaller series that I'm comparing it to should also converge. Okay? Similar, but kind of backwards, if the sum of A sub n, if the smaller series diverges, then any series that's larger, B sub n, should also diverge. So a smaller divergent series would imply, when I'm comparing to a larger series, that that series is also divergent. Okay, so in short, let me summarize this again. Try to take that in. I'll try to reiterate this as I go through examples, and you can always come back to this slide. But I kind of use these two bullets here as my little shortcuts, right? My little ways of understanding these. So the idea is this. Say I have the harmonic series, right? This guy I know diverges. We are able to show that. Then any series that's larger than the harmonic series should also diverge. I'm adding larger numbers up. So for example, if I have the harmonic series, I need some other larger series. Well, larger. What does it mean to be larger? The numbers I'm adding together are bigger. Okay? That means they have to be bigger, at least kind of far out in the future, right? We say for all n, but really what is most important is like, kind of as I'm adding these up, I'm adding numbers that are bigger, just plain and simple. So if I make the denominator smaller, that increases the size of the quotient, right? Since n is in the denominator there, I'm working with 1, 1/2, 1/3, 1/4, 1/5, so on and so forth. The numbers I'm working with, I need to compare to, or that I decide to compare to, kind of have to be larger numbers. So making the denominator smaller, for example, 1 over n minus 1, that would be like my Bn here and my larger series. The denominator is smaller, it's indeed larger. Okay, and since I know that 1 over n diverges, and it's smaller, then by the comparison test or direct comparison test, we say that this Bn should also diverge. That's it. So since I have a smaller divergent series and I'm comparing, and that's the series that I'm comparing to, 1 over n minus 1 should then also diverge. Okay? So this is kind of a backwards example where I started with a series to compare to tell me about a series that I didn't know about. Right? Typically, this goes kind of in the opposite direction. So what we'll say is if I start with a series, I'm going to try to find a series to compare to that I know about. Okay, so let's look at this again. 1 over 3 to the n plus n from n equals 1 to infinity. Okay? So we know this is like a geometric and harmonic series. Okay, so let's kind of dissect those, and I want to figure out if I'm comparing to the harmonic or geometric. So this guy, we're going to try to compare. We have two options: to compare to the harmonic or to compare to the geometric series, which is really more like 1 over 3 to the n. Okay, one of those converges, the other diverges. Which do we do? This is the harmonic. It diverges. This guy's geometric with a common ratio less than 1. That guy converges. So which is it? What do we do? Which is it? Well, so I've written in some inequalities here. These are both true. By removing, in number 1 here, by removing the 3n from the denominator, I've made the denominator smaller, right? 1 over n has a smaller denominator than 1 over 3 to the n plus n, which makes the fraction larger. Sorry. Let's go back. Which makes the fraction larger. And the same thing happens in case number 2 here. I've made the fraction larger because I've taken away the n in the denominator. This is very typical practice. We try to like remove some portion of our nth term to see what happens, and we remove it so that it looks like an nth term that we recognize, that would produce a p series or a geometric series. So when I remove either 3 to the n or n, I'm comparing to then these two different series that I know the convergence or divergence of. Okay. So which is it again? Which is right? Well, the direct comparison test doesn't say anything about a larger divergent series. Okay? That means that number 1 is out. Comparing to the harmonic series here doesn't really get me anywhere. Yes, it's true, I know that the harmonic series diverges. However, when I compare to that, I'm working with now a larger series that I know diverges, which doesn't tell me anything about the smaller series. Okay? It's very easy to get hung up on that. But because 1 over 3 to the n plus n is smaller than a divergent series, comparing it that way doesn't give me any information. However, number 2, when I compare in the case where I removed n from the denominator, I'm comparing to 1 over 3 to the n. That is a larger convergent series. So since a sub n, my 1 over 3 to the n plus n, is smaller than 1 over 3 to the n, here I'm actually kind of now labeling what I've chosen for a and b, or a sub n and b sub n. Since that's the case, since I have that following inequality, I need to see an inequality there in order to actually use a direct comparison. And I know that this 1 over 3 to the n is geometric and it converges. Then by the direct comparison test, I can say that the series that I started with also converges. Okay? So we play this little game where we take away pieces parts, or we add pieces parts, or we try whatever we can do to compare to a series that we know about. Sometimes the comparison that we make doesn't get us anywhere. Okay? You have to be okay with that. The number 1, case 1 here, didn't apply. The direct comparison test didn't work with comparing to the harmonic series. It's true to say that the harmonic series is larger, sure, but that doesn't give us anything. I compared to a geometric series that's larger. And notice I didn't just make up 1 over 3 to the n. It was embedded in the series already, or in the nth term already. I didn't say, 1 over 2 to the n, or 1 over 6 to the n. No, I used 1 over 3 to the n, something that was already part of my series. So very frequently, I'm just taking away pieces parts to find something that's similar. Okay, let's do another example. Determine whether the series 1 over n minus the square root of n converges or diverges. Okay, this one I have to start at 2 because when n is 1, I have an undefined term. That's nonsense. That won't happen. So I want to try to find something to compare to. Let's try what happens when I take away, for example, the square root of n, or minus square root of n. I compare to 1 over square root of n. I compare to the harmonic series here. By removing this minus square root of n piece here, I've made the denominator larger, right? If you want to write off to the side, you can. N minus square root of n is smaller than n. It's true. I'm taking away something on the left side, which makes the left side smaller. Right? In a quotient, a smaller denominator means larger. So that's why I can say that 1 over n minus square root of n is larger than 1 over n. Okay? This is the difficult thing about this test. It seems like you're just making things up and you're just writing down the inequality the way that you want it to work. It has to be true. The inequality has to be true. I can't just write things down, right? But because I have a smaller denominator on the left side, that's a larger fraction, okay? So what I'm able to say then is, okay, notice also, I've written over some of my work here. I apologize. Just give me a second. I'm going to erase what I just wrote. This I want to go away. So notice what happens here. Why didn't I take away the n? Why didn't I compare to 1 over the square root of n? Well, taking away the n there is a little bit more difficult, right? I'd be dealing with 1 where'd it go? Sorry. 1 over minus the square root of n. And I can't do that because a sub n and b sub n have to be bigger than 0. I can't compare to that minus square root of n down there. Okay? I have to compare to positive things because that's the way the test is defined. So what I have is the harmonic series. That's my smaller series in this case, and I was using orange before, so I'll continue that. It's smaller than the larger series, 1 over n minus square root of n. That's my b sub n, a sub n. I know the harmonic series is divergent, and I have a smaller divergent series. That means that the larger series should also diverge. So my punchline here, since 1 over n diverges, and 1 over n is smaller than 1 over n minus square root of n, by the direct comparison test, my series, then 1 over n minus square root of n, should also diverge. Okay? So it's a little tricky. It is really fast if you can see what the correct series to compare to is. Okay? It takes a little bit of time to get used to. A lot of these inequalities are difficult to wrap your head around, but once you kind of get the idea of how these things go, it's a nice, quick, easy test to apply, and it works really nicely. But you just have to keep in mind that you can only compare, or you can only have really a smaller divergent series or a larger convergent series in order for this test to work well. Okay? Another example. I'm just going to reuse the example I did before, 1 over 3 to the n now, and this time it's minus n. Okay? So this is going to change some things. When I try to compare the same way, what did I do last time? I took 1 over 3 to the n minus n or plus n, and I compared it to 1 over 3 to the n. But notice my fractions are different this time. When I take away n in the denominator, right, when I'm subtracting n, I've made the denominator actually smaller instead of larger, right? Before I was adding n in the denominator, which made the denominator larger, which made the whole fraction smaller. This time, however, my inequality goes the other way because 3 to the n minus n is smaller than 3 to the n. So a smaller denominator means I have a larger fraction. This time, I have a smaller convergent series. I'm just going to rewrite my inequality here. 1 over 3 to the n is actually smaller than 1 over 3 to the n minus n. Okay? So changing just a small sign or looking at a slightly different example might really have a large effect. So the way this inequality goes now does not apply to my direct comparison test. We have a smaller convergent series, which implies nothing. It doesn't tell me anything. With the direct comparison test, I need a larger convergent series. I can't just write the inequality the other way. That's not true. Okay? So, direct comparison test does not apply here. Doesn't work. Let's look at another similar example, say 1 over n plus 5 from 1 to infinity. I forgot to write the infinity there. Sorry. If I compare this series, that's most like the harmonic series, right? If I just take away the 5, I make the series larger because I've made the denominator smaller by removing that 5. So 1 over n is actually larger than 1 over n plus 5. Here's another situation where I'm comparing directly to a series that I know about, But the direct comparison test doesn't really give me anything because this is a larger divergent series. That's a larger divergent series, and it doesn't tell me anything. So in both of these situations, the direct comparison test doesn't work. But there is another test that we can do, and that's the second test for this section. There's another test that will help us in situations like this, okay? And it's called the limit comparison test. This is for when the direct comparison test is difficult or just doesn't apply. Like in the previous situation here, I've got two inequalities that don't go the way that they should for the direct comparison test. And there's nothing I can do about it except for apply a different test. Okay. So the way this works here, I'll lay things out here. If I have two positive nth terms, if a sub n and b sub n are both positive, and I take a limit of the quotient when I stack the two nth terms. Okay, so the limit as n goes to infinity of a sub n divided by b sub n. Basically, the way this works is I'm looking at the ratio of the nth terms. Okay, a sub n or b sub n, which one of the two you're going to know about. Okay, and I think you'll see that in some examples. If this limit is L, where L is positive and finite. In other words, if L is between 0 and infinity, that's what it means to be positive and finite. Okay? It's got to be smaller than infinity, it's got to be finite, and it's got to be bigger than 0. It's got to be positive. Then this is another one that's similar to the integral test, where we have kind of a coupled convergence or divergence. This means that the sum of a sub n and b sub n either both converge or they both diverge. So it's coupled. So I have to know about one of these two series. And then when I take their limit of a sub n over b sub n, I get a result that's finite and positive. I can say that either both of the series converge or diverge. It just depends on the series that I'm comparing to. Note here that it doesn't matter whether I have a sub n on the numerator or b sub n. Excuse me. If L is finite and positive, then so is 1 over L. Okay? So therefore, it doesn't matter if b sub n is my numerator or a sub n is your numerator. You'll see me do both. You can pick a scheme and kind of stick with it. It doesn't so much matter. I'll do an example here. So this test is a little different. It doesn't give us kind of like right away convergence or divergence. We have to go through and take a limit. And again, I'll try to accent and outline where this is useful. So again, back to this example. We determined that we cannot directly compare here because the direct comparison test the inequality doesn't go the way we want it to. Okay. So again, we kind of have two choices. We can try to compare to the geometric or the harmonic series. So let's try our limit comparison test to 1 over n or 1 over 3n. Let's set things up first with 1 over n. Okay. So the way this would work is if this limit is finite and positive, since I'm comparing to a series that I know diverges, the harmonic series I know diverges, that would show me that the series 1 over 3 to the n minus n would also diverge. So it's coupled because 1 over n diverges, so would 1 over 3 to the n minus n. So let's dissect this limit. You can think about me having an a sub n and b sub n already. I don't really choose an a sub n and b sub n here because I think it's confusing. Basically, I've picked a series that's similar to the series that I'm given, that I'm starting with, and I set up this limit. It doesn't matter if the 1 over n is in the numerator or denominator, and I'll show that a little later. So since I'm dividing a quotient by a quotient, I'm going to multiply by the reciprocal here, which really just puts an n in the numerator, right? I have n over 3 to the n minus n. both here, the numerator and denominator, are approaching infinity as n goes to infinity, right? As n goes to infinity, the numerator is an infinite, approaches infinity. The denominator, 3 to the n, grows much faster than just n. So the denominator should also go off to infinity. This implies that I can use L'Hopital's. So I take derivatives. Derivative of the numerator is 1. Derivative of the denominator is 3 to the n natural log of 3 minus 1. Now I only have one n, that's down here in the denominator, and as n goes to infinity, that's going to grow and grow and grow. So the denominator keeps growing, the numerator stays at 1. This limit is 0. That's my L, but it's not positive. This is not a positive limit. It's 0. That means the limit comparison test does not apply. What that means is that comparing to 1 over n was not a good comparison. Okay? So you know you've made an incorrect comparison when your limit comes out to be 0 or infinity or negative, or something happens where you get a limit that's not positive or finite. Okay? So we've made the incorrect comparison. That's how I know I want to switch and go back and compare to the geometric series, right? Just changing the sign. Remember last time we had 1 over 3 to the n plus n. It shouldn't all of a sudden really change too much by changing that plus to a minus. It changes the test we use, but the convergence should probably be pretty similar. So now let's set up a limit with the geometric series. So again, it doesn't matter which is on top or the bottom here, but I have 1 over 3 to the n in the denominator. When I multiply by the reciprocal, that 3 to the n shows up top. And to evaluate this limit, I could use L'Hopital's. Unfortunately, I would have to do it twice. And you can go through that if you like, but what I'll go through and do here is I will divide both the top and the bottom by 3 to the n. And what that creates for me is a 1 in the numerator and a 1 minus n over 3 to the n in the denominator. N over 3 to the n we can show goes to 0. Remember, 3 to the n grows faster than n. That limit goes to 1 then, because 1 over 1 minus 0. That is a finite and positive limit. So comparing to 1 over 3 to the n is a better comparison here. Though we're using limit comparison, it's a better comparison than the harmonic series 1 over n. So since the sum of 1 over 3 to the n converges, then by the limit comparison test, 1 over 3 to the n minus n also converges. Okay? So again, we have that coupled comparison. When we were comparing two limit-wise to a series that converged, and we got a finite positive result, that means the series that we start with also converges. Okay? So it's not this direct comparison that I had before. I'm not just saying, oh, I have a larger convergent series, so my series converges. It's true that I'm comparing to a convergent series. So as long as the limit is finite and positive, then yes, the limit comparison test applies and I'm good to go. I want to do another example. Last one here. Compared to something a little bit more wild, the sum of n squared over 2n cubed plus 2n minus 4. So another situation where direct comparison might not be so nice, right? What we look for here is what goes on for large n. For large n, how does this thing behave? The series kind of works like n squared over n, or 1 over n. I'm looking for leading terms here. So I'm really looking for this n squared and 2n cubed. Those are the leading terms for large n. Okay, so far out in my series, the terms are going to really look like that 1 over n there. Notice that the direct comparison test is a little bit more difficult here. If I have n squared over 2n cubed plus 2n minus 4, That's similar to 1 over n, yeah, but how does it go? Is it smaller? Is it larger? I don't know. It's a little bit tough to say, because in the denominator, right, I'm adding 2n and I'm subtracting 4. I've also got an extra coefficient of 2 outside the n cubed. There's a lot going on. This is set up nicely for the limit comparison test. Okay? And that's just because the direct comparison is slightly difficult. We could probably make an argument about a direct comparison here. I just think it's easier to kind of go right to, in a situation like this, to limit comparison. We know that this thing behaves eventually like 1 over n. Okay? So that's what we're going to try to compare to. And it doesn't matter whether 1 over n is in the numerator or denominator here. So I put it downstairs. Again, doesn't matter. It might be a little bit easier if you put it in the numerator. That might be something you try. So for right now, I'll stick with what I've got. When I take n squared divided by 2n cubed plus 2n minus 4 and divide that by 1 over n, it's the same as multiplying by the reciprocal. I have an n cubed in the numerator now, and that polynomial in the denominator. You could apply L'Hopital's here, but again, it would require a couple applications, at least 2, in order to get a result. So what I do is I divide both top and bottom by the highest power of n in the denominator. Okay? You could divide through by 2n cubed, that also works, but n cubed will suffice. What happens here, in fact, really, that's enough to just look at the powers. Since the leading powers are the same in the top and the bottom, this limit should be the coefficients of the numerator and denominator. It should be 1/2. Let's show that happens. When I divide the numerator by n cubed, I get a 1. And the denominator by n cubed, I get a 2 plus 2 over n squared minus 4 over n cubed. Both of those guys are going to go to 0 as n goes to infinity. So my limit should give me 1 over 2 plus 0 minus 0, or a half. That's definitely finite, and it's definitely positive. So the limit comparison test will apply. I have chosen a good series to compare to. So since 1 over n, the harmonic series, diverges, my series that I'm comparing to should then also diverge by the limit comparison test. This series also diverges. Okay, so the direct comparison test tends to be quick, and if you can see directly what series to compare to, then it usually goes fast, and it's not too bad. It's just a little bit abstract because these inequalities tend to be difficult to work with. The limit comparison test tends to be a nice fallback. If you're having trouble with the direct comparison test or not sure what to compare to, or the inequality doesn't go the way you want, that's kind of an indicator that you want to apply the limit comparison test. I just have to have a limit that's finite and positive. Okay? That's it for this video. Thanks for watching.